Right now, Earth is moving through darkness inside something we cannot see. It is not a wall. It is not a roof. It is not a place marked in the night sky. But it helps decide what reaches our world, what is turned away, and what quietly changes before anyone on the ground can feel it. Most of the time, space feels distant from ordinary life. We look up, see stars, and think of them as lights far away. But the space around our planet is not separate from us. It touches our atmosphere. It shapes the conditions above our heads. And in ways we are only beginning to measure, it connects Earth to the wider galaxy. This story is not about panic. It is not about a disaster waiting tomorrow. It is about a slow, invisible crossing, and the strange realization that our solar system is not moving through emptiness at all. If you enjoy calm, long-form documentaries about space, science, history, and the mysteries that sit at the edge of what we understand, subscribe to The Last Signal on YouTube. It helps the channel reach more people who want stories told slowly, carefully, and without the noise. Now, let the sky become larger than it looked a moment ago. The sun's protective domain is the invisible region that carries every planet through interstellar space. Earth is not standing still in a silent, empty dark. It is moving with the sun, with the moon, with Mars, with Jupiter, and with every small world caught by our star's gravity. Every ocean moves with it. Every city moves with it. Every forest, desert, satellite, aircraft, and sleeping human body is being carried through a medium most people never picture at all. That medium is the interstellar medium, the thin mixture of gas, dust, particles, and magnetic fields that fills the space between stars. To human senses, it would seem almost like nothing. There would be no wind against your face, no sound, no visible fog, and no pressure you could feel with your hands. But on the scale of a solar system, even material this thin can matter. The reason Earth is not exposed to that material directly begins with the sun. Our star constantly releases a stream of charged particles into space. This stream is called the solar wind, and it flows outward in every direction, far beyond the orbit of the planets. It is not ordinary wind. It is made of charged particles, moving through space with the sun's magnetic field carried along inside it. As this outflow spreads, it inflates a vast region around the planets. That region is called the heliosphere. It is often described as a protective bubble, but that picture can be misleading if it sounds too solid. The heliosphere is not a glass shell. It is not a wall. It is a changing magnetic and particle environment shaped by the pressure of the solar wind pushing outward and the pressure of interstellar space pressing inward. A useful way to picture it is a quiet vessel moving through dark water. The sun is not merely a light at the center of the vessel. It is also the engine, constantly sending material outward and holding open a space around the worlds inside. The planets move within that solar domain, protected not by metal or stone, but by a field of moving particles and magnetism. Outside, the interstellar medium presses from every direction. It is thin beyond ordinary imagination, yet it is not powerless. A lamp gives another comparison. Near the flame, warmth dominates the air around it. Farther away, the cold room begins to win. The heliosphere works in a similar balance, with the sun's outflow dominating close to the planets and the surrounding interstellar environment gaining influence near the outer boundary. This matters because space contains particles that would otherwise reach the inner solar system more easily. Among them are galactic cosmic rays, high-energy particles that arrive from distant, violent regions of the galaxy. Some are born from the remains of massive stellar explosions. Others come from extreme astrophysical environments, where matter is accelerated to powerful energies. The heliosphere does not stop all of them. No natural shield does that completely. But it changes how many arrive, how easily they move inward, and how strongly they affect the environment around Earth. That filtering matters for spacecraft electronics, for astronauts beyond Earth's magnetic field, and for the chemistry of the upper atmosphere over very long time scales. It also matters because Earth has more than one layer of defense. The Sun's magnetic shelter filters part of the incoming particle environment first. Earth's own magnetic field bends many charged particles away. The atmosphere absorbs much of what remains before it can reach the surface. Life exists under all of those layers at once. From the ground, this protection feels ordinary because it is invisible. A person can stand under a clear night sky and see only stars. There is no sign overhead that the planet is inside a vast, moving boundary. There is no visible edge where the sun's influence weakens and the galaxy outside begins to press harder. There is only darkness, distance, and the old illusion that empty space is truly empty. But the solar system is not isolated. It is moving through a changing environment, wrapped in a region created by the sun and shaped by the material beyond it. And once that picture changes, the familiar diagram of planets circling a star becomes something stranger. It becomes a moving system inside cosmic weather. The sun's magnetic shelter is not fixed in place. It changes shape, pressure, and strength as the sun itself changes. This is one of the most important facts about the solar system's outer boundary, because it means the region around the planets is not a permanent structure. It is a balance. On one side, the sun sends the solar wind outward. On the other side, interstellar space presses back. Between those two forces, the heliosphere expands, tightens, bends, and adjusts. The solar wind does more than carry charged particles through space. It also carries the sun's magnetic field outward, pulling magnetic field lines into the solar system, like long threads drawn from a spinning source. Those field lines do not sit neatly in one place. They are dragged, twisted, stretched, and shaped by the motion of the sun and the flow of charged particles around it. That turns the heliosphere into something more complex than a simple cloud. It is a moving magnetic structure. It has pressure. It has direction. It has areas where particles are guided, slowed, scattered, or partly blocked. And because it depends on the sun's activity, it rises and falls with the rhythm of the star that creates it. Over repeated solar cycles, the sun becomes more active and less active. During more active periods, stronger solar wind tends to push outward with greater force. When that happens, galactic cosmic rays have a harder time reaching the inner solar system. They are still there. They still arrive from far beyond the sun. Yet their path inward becomes more difficult because the magnetic environment around the planets has become stronger and more disturbed. During quieter solar periods, the opposite pattern often appears. The solar wind weakens, the outward pressure drops, the boundary can draw inward. Particle counts near Earth can rise, especially for the kinds of cosmic rays that are still affected by the sun's magnetic reach. This does not mean the shield turns off. It means the filter changes. A filter can become more open without disappearing. A door can let in more cold air without falling from its hinges. The same basic idea applies here, though on a scale that reaches far beyond ordinary imagination. For the listener on Earth, the change is not something seen in the sky. The stars do not move differently from night to night. The moon does not appear behind a new haze. No visible border slides closer to the planets. Instead, instruments measure pressure, particle counts, magnetic direction, and the faint signs of a boundary moving under forces too spread out for human senses. Picture that boundary slowly widening and narrowing around the planetary system. There is no skin around it. There is no surface to touch. There is only the pressure of particles, the shape of magnetic fields, and the long negotiation between the sun and the surrounding medium. For years, the outer domain may hold farther out. Then the sun quiets, and the structure tightens. Then activity rises again, and the outward pressure strengthens. The whole region breathes without lungs, expands without muscle, and contracts without sound. That breathing matters because it changes the path of incoming particles. Galactic cosmic rays are not all the same. Some are so energetic that even the sun's magnetic influence can do little to stop them. Others fall into a range where the solar wind and magnetic field can still affect how easily they enter the inner system. Those middle-range particles are important because they can reach Earth's neighborhood in changing numbers. They can interact with spacecraft. They can contribute to the radiation environment beyond Earth's magnetic field. They can begin chains of interaction in the atmosphere if they reach far enough inward. Scientists can measure parts of this pattern directly. They have seen how particle levels respond when solar activity changes. They have measured changes in solar wind pressure across recent decades. They can compare the sun's quieter periods with times when the cosmic ray count rises. But the deeper cause behind every long-term variation is harder to separate. Some changes come from the sun itself. Some may be shaped by the interstellar material around the solar system. Some may involve both, acting together in ways that are difficult to isolate from inside the very system being affected. That is why the question becomes serious without becoming simple. The heliosphere is not merely a shield that either works or fails. It is a living balance of pressures, fed by a changing star and tested by a surrounding medium that is not perfectly still. When the sun pushes strongly, the solar domain holds more ground. When the sun becomes quieter, the edge can become more vulnerable to whatever presses from outside. The most important risk is not weakness alone. It is weakness meeting pressure at the same time. The local interstellar cloud is the material the sun is moving through right now. It is not a cloud in the ordinary sense. It does not hang above us like weather. It does not glow around the planets. It would not look like mist outside a spacecraft window. By human standards, it is almost impossibly thin. If a person could somehow stand inside it, there would be no feeling of air, no dampness, no visible haze, and no sound moving through it. Yet scientifically, it is real material. It contains gas. It contains dust. It carries magnetic fields. It has motion, temperature, pressure, and structure. That is what makes it important. The solar system is not crossing a perfect vacuum. It is moving through a surrounding medium that can press, flow, vary, and interact with the sun's own magnetic domain. One of the strangest things about this region is that it can be described as hot and almost empty at the same time. That sounds contradictory only because human experience links heat with density. A hot room feels full because air molecules are constantly striking skin. A flame feels intense because many particles and photons are delivering energy in a small space. The local material around the sun is different. Individual particles can move quickly, so their particle temperature is high. At the same time, those particles are separated by distances that make ordinary air seem crowded beyond belief. It is like a faint fog inside an almost empty room, except even that comparison gives it too much substance. No human-built vacuum chamber would make this material feel thick. No breath could move through it. No hand could sweep it aside. Still, for a structure as large and delicate as the sun's outer boundary, even this faint material has weight. Pressure in space does not need to feel strong to matter across enormous distances. A tiny push, spread across a vast frontier, can change where one influence ends and another begins. That is why scientists care about the density, flow, and magnetic direction of the surrounding medium. The question is not whether the cloud would feel dense to a human body. It would not. The question is whether it is dense enough, uneven enough, or magnetized enough to compress the sun's protective domain over long periods. Researchers study this environment from inside it, which makes the task unusually difficult. They cannot step outside the solar system and look back at the whole structure from a distance. Instead, they infer the surrounding material through signals that pass into or through the sun's domain. Some of those clues come from neutral atoms. Atoms such as hydrogen and helium can enter from interstellar space because they are not electrically guided in the same way charged particles are. By measuring them, scientists can learn about the flow of the material outside the sun's reach. Other clues come from distant stars. As starlight passes through thin interstellar gas, some wavelengths are absorbed along the way. Those missing traces act like fingerprints, showing what kind of material lies between the star and the observer. This is a difficult way to map a neighborhood. It is less like seeing a road ahead and more like studying faint marks on light after it has crossed the dark. From those marks, researchers know the surrounding medium is not perfectly smooth. It has variations. It has flows. It may contain denser pockets or narrow filaments. Its magnetic field may change direction or strength across regions that are still hard to map in detail. That matters because a smooth cloud and an uneven cloud would affect the solar boundary differently. A smooth flow would press more steadily. A denser pocket could push harder for a time. A magnetized filament could change how particles move near the edge. The difference may sound small, yet small differences become important when the entire solar system is the object moving through them. This is where caution is essential. Scientists can measure the local environment around us. They can identify structure in the nearby interstellar medium. They can compare those measurements with models of how the sun's domain should respond. What they cannot yet do is produce a perfect forecast of every pocket, flow, and magnetic fold that lies ahead. The path in front of the sun is not mapped with the clarity of a weather radar over a city. It is inferred from particles, starlight, spacecraft data, and models that improve slowly as more evidence arrives. So the surrounding cloud is not a visible wall waiting in the dark. It is not a sudden threat. It is a thin, structured medium already around us, already touching the outer boundary of the sun's influence, and already part of Earth's larger environment. The unsettling part is not that the solar system has entered something unknown. It is that the solar system has always been moving through material like this, while only recently have our instruments become sensitive enough to notice how much that material matters. The sun carries its planets through a medium it can feel, while the full shape of the route ahead remains beyond clear sight. The Voyager probes began as travelers to the outer planets, but their most haunting work came after the planets were already behind them. They were built during the late Cold War, when space exploration still carried the weight of national ambition and technical risk. Their first task was to pass the giant worlds and send back measurements from places no spacecraft had studied so closely before. Then, slowly, after the main planetary mission had become history, the probes kept going. They crossed beyond the familiar architecture of the solar system and moved toward the outer reach of the sun's influence. What began as a planetary mission became something else. It became a test of whether the sun's boundary could be measured directly. For decades, the heliopause had been more than a simple line on a diagram, yet no instrument had touched it from the outside. The heliopause is the outer boundary, where the solar wind gives way to the interstellar medium. It is not a metal fence around the planets. It is not a clean edge drawn through space. It is the region where the sun's outflow loses its dominance, and the surrounding galactic material becomes the stronger environment. Voyager 1 reached that boundary first. Voyager 2 crossed later, in a different direction, giving scientists a second point of comparison. That difference mattered immediately. If both probes had measured exactly the same conditions, the boundary might have seemed simpler. Instead, their data showed a more complicated structure. The broad pattern was similar, but the local details were not identical. The sun's domain did not end like a perfect sphere. It ended more like a changing frontier, with conditions that depended on direction, magnetic structure, and local particle populations. As the probes approached and crossed the heliopause, the particle environment changed. The familiar signs of the solar wind faded. Particles from interstellar space became more prominent. Plasma measurements began to tell a different story about the material surrounding the spacecraft. Magnetic field readings added another layer of difficulty, because the field beyond the boundary did not behave as simply as many older expectations suggested. These measurements did something important. They turned the outer edge of the sun's influence from a model into a place. The boundary was real. It had texture, pressure, direction, and measurable change. It was no longer only a theoretical surface placed far beyond the planets. It was something a machine could pass through, record, and report back from. That reporting is almost difficult to imagine calmly. Far beyond the planets, a spacecraft small enough to disappear inside any ordinary hangar continued to send signals home. The signal was weak. It moved across distance for many hours before reaching antennas on Earth. By the time the information arrived, it had crossed the space between a human-built machine and the planet that had launched it several decades earlier. There was no camera showing a glowing border. There was no dramatic crossing marker. Only particles, fields, plasma waves, and changes in the numbers coming back to mission teams. In that quiet stream of data, scientists watched the sun's protective domain become measurable at its edge. The probes were like two thermometers placed at different points around an enormous weather system. One reading could prove that conditions had changed at one location. A second reading could show whether the same pattern appeared elsewhere. Together, they offered something priceless, but still incomplete. Two paths through the outer boundary cannot map an entire structure wrapped around the planetary system. They cannot reveal every flank, every fold, every region where interstellar pressure presses differently. They cannot show how the boundary changes across all directions at once. They are narrow tracks through a region larger than any mission was originally built to understand. That limitation is part of their value. It reminds scientists that direct evidence is rare. A model can estimate where the heliopause should be. A telescope can infer structure from particles or light. A map can suggest the shape of the surrounding interaction. Only a spacecraft crossing the boundary can report what the environment feels like at that point in space. And even then, the report is partial, local, and tied to the instruments still alive on board. The Voyager probes are aging now. Their power is limited. Their instruments have been managed carefully, one system at a time, as engineers try to preserve the last flow of interstellar data. Each remaining measurement carries unusual weight because no replacement is already waiting at the same distance. No fleet surrounds the heliopause. No wide sensor net watches the sun's boundary from all sides. Humanity's most direct evidence still comes from a pair of old machines moving outward through darkness. They were not built to answer every question about the interstellar medium. They were not designed as a complete map of the solar boundary. Yet they changed the question forever by showing that the sun's edge could be crossed and measured. The farther they travel, the more fragile their voices become. And still, from beyond the solar boundary, they continue to report that the space outside the sun is not empty silence, but a measurable world of particles, pressure, and magnetic force. The interstellar boundary. Explorers studied the solar system's edge without traveling anywhere near it. It worked from close to Earth, looking outward by catching particles that had returned from the distant boundary. That made the mission unusual from the beginning. It was not a probe moving through the heliopause like Voyager. It was more like an instrument, listening for echoes from the edge of the sun's domain. The particles it measured were called energetic neutral atoms. That phrase sounds technical, but the basic idea is simple. Near the outer boundary, charged particles from the sun and charged particles from interstellar space can interact. In some of those interactions, an electric charge is exchanged. A particle that was once guided by magnetic fields can become neutral. Once neutral, it is no longer steered in the same way. It can travel inward across enormous distance in a straighter path, carrying information from the region where it was formed. By detecting those returning particles, the interstellar boundary explorer could build a picture of the heliosphere's outer interaction zone. It was not taking a photograph in ordinary light. It was not seeing a glowing shell around the solar system. It was mapping particle arrivals across the sky and turning those measurements into a full sky view of the boundary. This was like learning the shape of a distant surface by studying what came back from it. The method was indirect, but it was powerful. It gave scientists a way to study parts of the outer solar domain that no spacecraft had physically crossed. Then the first major maps revealed something unexpected. A bright, ribbon-like band stretched across the particle map. It was not a decoration. It was not a visible stripe in the night sky. It was a concentration of energetic neutral atoms arriving from a specific region of the boundary interaction. Earlier, models had not placed a feature like that across the map. The map had drawn something theory had not. For scientists, this mattered because the outer heliosphere was supposed to be difficult, but not in exactly that way. The broad interaction between the solar wind and the interstellar medium was already known. The sun pushed outward. The surrounding material pressed inward. Particles changed energy, direction, and behavior near the boundary. But this band suggested that the external magnetic environment was shaping the interaction more sharply than expected. The leading interpretation connects the feature to the interstellar magnetic field outside the heliosphere. In certain regions, the geometry of that field may line up in a way that makes energetic neutral atoms more likely to arrive from that direction. That does not mean the explanation is fully settled. The feature is real in the data, but its exact physical origin remains an active research question. There are models that explain parts of it. There are observations that constrain what it can be. There are still details that do not reduce to one clean answer. That uncertainty is the important part. The outer boundary is not behaving like a simple surface with uniform pressure around it. It is responding to direction, magnetic structure, particle populations, and changes over time. The brightness and position of the feature have also shifted as observations continued. That means the interaction zone is not only structured, it is changing. For a moment, picture the scientists studying that full sky particle map. There is no spectacular photograph on the screen. No colored nebula floats behind the planets. No border glows at the edge of the solar system. Instead, there are measured arrivals, converted into a pattern. And inside that pattern, a band that should not have looked so clear. The surprise is quiet. It lives in the difference between what the instruments recorded and what the models had prepared them to see. This is how space often reveals itself, not with a visible sign, but with a mismatch. A number comes from the wrong direction. A pattern gathers where a smoother spread was expected. A boundary that seemed understandable becomes more detailed under better instruments. For the question of interstellar cloud crossing, that detail matters. If the magnetic field outside the sun's domain has structure, then pressure from the surrounding medium cannot be treated as simple and even. If the boundary responds differently in different directions, then forecasts become harder. If the outer interaction changes over time, then a single map is never the whole answer. The Interstellar Boundary Explorer showed that the sun's edge is not merely far away. It is complex in a way that can reach back toward Earth through particles born near the boundary. The ribbon became a diagnostic mark on the outer solar domain, a moving sign that the interaction between the sun and interstellar space was more organized than expected. It did not solve the heliosphere. It made the mystery sharper because it proved the edge had drawn a line that older models had not seen coming. The shape of the solar boundary is still not fully settled. That may sound strange, because the heliosphere is one of the largest structures connected to the sun. But size does not make something easy to understand. A structure can surround every planet and still remain difficult to measure, especially when humans are trapped inside the very system they are trying to describe. For a long time, one picture seemed natural. If the sun moves through interstellar material, then its outer domain should have a rounded front and a long trailing region behind it. That model looked something like a comet. The front faced into the flow. The back stretched away from it. It was an intuitive idea because moving objects often leave wakes behind them. A boat cuts through water and leaves disturbed motion in its path. A fast object moves through air and shapes pressure around its nose and sides. In the same general way, scientists pictured the sun pushing through the surrounding medium, with the heliosphere drawn out behind it into a long tail. That picture made sense as a first approximation. It gave the solar system a front, a wake, and a direction of motion. It also helped explain why the interstellar medium would not press on every part of the boundary in exactly the same way. But newer models and observations have complicated that image. Some research supports a shorter, rounder, or crescent-like structure. In that view, the heliosphere is not simply a comet shape with an extended tail disappearing far behind the planets. It may be more compact. It may have side regions shaped by the solar wind, the sun's magnetic field, and the magnetic field of the interstellar medium beyond it. The difference is not just artistic. It changes what the boundary means. A long-tail model suggests one kind of response to outside pressure. A compact or crescent-like model suggests another. If the solar domain is stretched far behind the sun, material and particles may move around it differently than they would around a shorter, rounder structure. If the sides are shaped into lobes or flanks, then the most exposed regions may not be where a simple diagram would place them. Geometry becomes physics. The outline decides how pressure is distributed. It decides where charged particles are guided. It decides which parts of the outer boundary absorb the strongest contact with interstellar material. This is why scientists do not treat the shape debate as a minor detail. It affects how the whole system filters incoming particles. It affects how the outer region responds when the surrounding medium changes. It affects how researchers interpret the narrow paths measured by Voyager 1 and Voyager 2. Those spacecraft gave direct evidence, but they did not give a complete shell around the sun. They crossed in limited directions. They measured local conditions. They did not surround the boundary from all sides. So the disagreement remains open with respected researchers testing different models against spacecraft data, particle maps, and magnetic field measurements. Now picture the solar domain from outside, as if it were finally visible. Ahead of the sun, there is a compressed front where the surrounding medium meets the outward push from our star. To the sides, the boundary may curve, bend, or fold in ways shaped by fields no eye could see. Behind it, there may be a trailing region, but perhaps not the long, smooth tail once imagined. The whole form would be less like a simple drawing, and more like a pressure pattern, wrapped around motion. It would not be bright. It would not have a clean surface. It would be known by particles, field directions, and the way material changed as it crossed invisible thresholds. That same uncertainty matters when scientists consider interstellar dust. Dust from outside the solar system has been detected inside the planetary region. Some of it has been measured by spacecraft. Some has been studied through missions connected with collecting or identifying tiny particles from space. Stardust, Cassini, and Ulysses are among the mission names that can appear in this discussion, though each one measured only part of a much wider picture. The key point is simple. The heliosphere is a filter, not a sealed room. It lets some material through while altering, redirecting, or reducing other material. Interstellar dust proves that the outside does not remain perfectly outside. The current levels are not a crisis for Earth. They are not a sign that the sun's protection has failed, but they show that the boundary is selective, permeable, and dependent on conditions. If the surrounding medium becomes denser, more turbulent, or differently magnetized, then the filtering behavior could change. How much it changes depends partly on the shape of the boundary itself. A long comet-like structure might distribute pressure across a different region than a compact crescent-shaped one. A rounded domain might expose its flanks differently than a drawn-out tail. A boundary with side lobes might allow particles and dust to enter through routes that a simpler model would underestimate. This is why the shape question sits at the center of the larger problem. It is not only about what the heliosphere looks like, it is about how the solar system meets the galaxy. A sealed wall would make the story simple. A smooth sphere would make it easier. But the evidence points towards something more active, more directional, and more dependent on the magnetic environment outside the sun. The solar boundary is a structure under pressure, and its shape decides where that pressure is felt first. Cosmic rays and the air above us meet in a place no human eye can watch directly. High above the weather, above the clouds, and above the routes of ordinary aircraft, a particle from deep space can enter Earth's atmosphere at tremendous speed. It may have traveled from the remains of a massive stellar explosion. It may have come from a region near a pulsar, or from another energetic environment where matter is accelerated across the galaxy. By the time it reaches Earth, its origin is usually no longer something that can be read like an address. What matters is what happens when it arrives. The particle strikes the upper atmosphere and does not simply stop. It collides with atoms in the air and creates a cascade of secondary particles that spread downward through the sky. One invisible arrival becomes many invisible descendants. A single spark becomes a branching shower, not made of water, but of energy, fragments, and reactions. This process is one reason Earth's defenses have to be understood as layers. The heliosphere filters part of the incoming particle environment before it reaches the inner solar system. Earth's magnetic field bends many charged particles away from the planet. The atmosphere then absorbs and transforms much of what survives the earlier barriers. No single layer does everything. Each one reduces, redirects, or changes part of the incoming energy. Together, they make the surface of Earth far calmer than the space around it. That is why heliosphere compression matters. If the sun's outer domain tightens or becomes less effective at filtering certain energies, more mid-range particles can reach Earth's neighborhood. The most energetic ones can be difficult for the sun to influence at all. Lower energy ones may already be filtered strongly. The important group sits between those extremes, where solar activity and magnetic structure can change the number that arrives. This does not mean the planet suddenly becomes unsafe. It means the background conditions above the atmosphere may shift. Those shifts can matter because the sky is part of the shield. When particle cascades form in the upper air, they interact with nitrogen and oxygen. Those reactions can produce nitrogen oxides, which can then influence ozone chemistry. Ozone is important because it helps absorb ultraviolet radiation from the sun. If its chemistry changes, even modestly or unevenly, scientists have to ask what that means for the balance of radiation reaching different layers of the atmosphere. This is not a simple chain where one cause produces one guaranteed outcome. Atmospheric chemistry is tangled. Solar activity changes. Weather patterns vary. Industrial pollution, volcanic eruptions, and natural cycles all complicate the picture. Still, the physical link between high-energy particles and chemical reactions in the atmosphere is real enough to deserve careful attention. Another question involves clouds. In controlled experiments, ionization can help tiny particles grow into the kinds of seeds that water droplets may gather around. That makes the idea of a cosmic influence on cloud formation physically plausible. Yet plausibility is not the same as proof at planetary scale. The real atmosphere is not a sealed laboratory chamber. It is moving, mixing, warming, cooling, and reacting in thousands of overlapping ways. Researchers still debate how large the cloud effect really is, and whether it is strong enough to leave a major climate signal compared with other forces. That distinction matters. A weak effect can be scientifically real and still not dominate the climate. A process can exist and still be too small, too variable, or too entangled with other systems to explain broad changes by itself. This is where calm language becomes necessary. Cosmic rays should not be turned into a single hidden cause for every climate shift or every biological change in Earth's past. The evidence does not support that kind of simple story. What the evidence does support is a more careful idea. The space environment can reach into the atmosphere through particle interactions, and those interactions can become part of Earth's long-term background conditions. There is also a biological dimension. Radiation can damage DNA. That is true in living tissue, and it is one reason astronauts and spacecraft crews face serious radiation concerns beyond Earth's protective magnetic field. At the surface, the atmosphere blocks much of the danger. Life on Earth is not exposed to interstellar space directly. However, across long spans of time, even changes in background radiation are worth studying, because mutation pressure is one of the ingredients in biological history. Some hypotheses suggest that changing cosmic ray levels may have influenced evolutionary rates or biological stress during certain periods. Those ideas remain speculative. Many evolutionary biologists would be cautious about giving cosmic radiation a central role when ecosystems, climate, geology, competition, disease, and chance all shape life at the same time. The fossil record is also incomplete, and broad biological patterns are difficult to tie to one distant cause. So the responsible view is neither dismissal nor alarm. It is attention. Picture the upper atmosphere during an ordinary day. Below, people walk through streets, fields move in the wind, waves break near shorelines, and aircraft cross the sky without anyone sensing a boundary overhead. Above them, particles enter, collide, split, and fade. The showers are silent. They leave no visible trail for a person standing on the ground. They are part of the invisible machinery that makes Earth both protected and connected to the galaxy. That connection does not mean an immediate catastrophe is waiting above the air. It means the conditions for life are not shaped by Earth alone. The sun, the planet's magnetic field, the atmosphere, and the surrounding interstellar environment all take part in deciding what reaches the surface and what never does. The serious question is not sudden extinction. It is whether a slow change in the cosmic background can alter the assumptions under which climate, chemistry, technology, and biology quietly operate. Stellar debris in the ocean floor is one of the strongest physical signs that Earth is not sealed away from the galaxy. The evidence does not begin with a telescope pointed into deep space. It begins in the slow darkness at the bottom of the sea. Far below, waves, storms, ships, and coastlines. Certain minerals grow over time in thin layers. They form so slowly that a human lifetime would barely mark them. Within those layers, scientists have found traces of iron-60. Iron-60 is a radioactive form of iron associated with massive stars and the debris of supernova explosions. It is not something Earth's surface should produce in meaningful amounts through ordinary processes. That is what makes it important. When iron-60 appears in ocean floor deposits, it acts like a stellar fingerprint pressed into the planet's own geological record. The material was once part of an environment far beyond Earth. It was connected to stars large enough to forge heavy elements and violent enough to scatter them into interstellar space. At some point in the recent geological past, some of that debris crossed the space between stars, entered the solar system, fell through Earth's atmosphere, and settled into the ocean. That simple chain is extraordinary. It means a star died somewhere near enough for its material to reach this planet. It means the galaxy did not remain distant. It left a trace in the sediment. The ocean floor remembered the stars. This does not mean a nearby supernova blasted Earth directly in some simple disaster. It does not prove that one stellar explosion caused a specific extinction, a specific climate shift, or a single dramatic turn in biological history. Science is rarely that clean when the evidence is spread across deep time. What the iron-60 evidence shows more securely is contact. Material from outside the solar system reached Earth and became part of its physical archive. That fact matters because supernova debris is not only dust. A nearby stellar explosion can also affect the radiation environment around the solar system. It can send energetic particles outward. It can alter the background of cosmic rays. It can change the kind of pressure that the heliosphere must withstand. If the sun's outer domain is already moving through a low-density region carved by earlier stellar explosions, then Earth's cosmic environment has a history shaped by events far beyond the planets. That larger region is often called the local bubble. It is a broad cavity in the interstellar medium shaped over millions of years by past supernovae and the winds of massive stars. The solar system has been traveling inside this lower density cavity for a very long time. Compared with denser regions elsewhere between stars, the local bubble is relatively thin. That matters because the heliosphere responds to what surrounds it. A thinner environment allows the sun's wind to hold a larger domain. A denser or more turbulent environment could press harder against that domain and change how particles enter the inner system. The local bubble is therefore not just background scenery. It is part of the reason the present solar boundary has the size and behavior scientists measure today. Again, caution is necessary. Iron-60 deposits do not give a complete history of every cosmic ray change Earth experienced. They do not provide a simple clock for every atmospheric or biological stress. They do not let scientists point to one layer and claim that one event explains an entire chapter of Earth's life. The geological record is complicated. Climate systems have many causes. Ecosystems shift through countless pressures at once. Volcanoes, ocean circulation, orbital cycles, plate movement, competition between species, and random survival all shape what happens on the surface. A stellar signal in the ocean floor is powerful evidence, but it is not a master key. Its strength lies in what it proves without exaggeration. It proves that material from nearby massive stars can reach Earth. It supports the idea that cosmic events can touch the planet physically, not just appear as points of light in the sky. It reminds scientists that the sun's protective domain is part of a larger galactic environment with its own history. Picture the deep ocean sediment forming one layer at a time. Above it, sunlight flickers near the surface, storms pass, animals migrate, and continents change too slowly for one generation to notice. Below it, chemistry keeps a quieter record. Grain by grain, layer by layer, the seafloor stores particles that fell from the atmosphere long after they crossed interstellar space. No witness saw them arrive. No ancient sky would have announced each atom as it settled into the water. Only later, through instruments sensitive enough to read the composition of old deposits, did the connection become visible to science. This is what makes the evidence so weighty. It joins the most distant kind of event to one of Earth's slowest records. A star explodes. Debris spreads through interstellar space. The solar system moves through the aftermath. A trace falls to Earth. The ocean keeps it. For the larger question of the heliosphere, this record changes the emotional scale of the problem. The boundary around the sun is not protecting Earth from an abstract universe. It is interacting with a galaxy that has already touched the planet in measurable ways. Our world has always lived inside that exchange. The air above us, the magnetic field around us, and the solar domain beyond the planets are all part of a layered defense against a galaxy that is active, uneven, and old. Iron 60 does not turn that fact into panic. It turns it into evidence. And that evidence says Earth has never been completely separate from the stars that made it possible. The sun's uneven wind begins close to the surface of the star, where heat, magnetism, and motion are tied together in ways no ordinary flame can match. This is where the solar wind has its origin. It does not simply appear at the edge of the planetary system. It begins near the sun itself, in the outer solar atmosphere called the corona. The corona is not calm air around a hot object. It is a thin, electrically charged environment where magnetic fields twist, stretch, open, and reconnect. From there, charged particles escape outward and become the flow that eventually fills the solar system. That flow is the beginning of the heliosphere's strength. If the outer boundary is the place where the sun meets interstellar space, then the corona is where the sun begins pushing back. For a long time, scientists could study the solar wind from a distance. Spacecraft near Earth could measure what had already arrived. Instruments farther out could examine how the wind behaved after it had traveled across the planetary region. But the source itself remained harder to reach. The sun is too hot, too bright, and too magnetically violent for ordinary spacecraft approaches. That is why Parker's solar probe changed the view. The mission was built to fly closer to the sun than earlier spacecraft, passing through regions where the solar wind is still being shaped. It had to survive near the outer solar atmosphere, where sunlight is harsh enough to destroy an unprotected machine. Its shield faced the star while instruments measured particles, fields, and motion around it. This made the probe less like a distant observer and more like an instrument placed inside the birthplace of the solar system. What it found showed that the flow is not smooth. One of the most important discoveries involved magnetic switchbacks. These are sudden folds or reversals in the magnetic field carried outward by the solar wind. A field line that seemed to point one way can suddenly bend back, kink, and then return again. The comparison is imperfect, but it helps to picture a wire carrying current that has been sharply folded in places. The direction remains part of the same larger system, yet locally it has twisted into a surprising shape. In the solar wind, those folds are not decorative. They tell scientists that the magnetic structure leaving the sun is turbulent from the start. The flow carries hidden eddies, sudden turns, and internal patterns that can survive as the wind expands outward. This matters because the heliosphere is made from that wind. A simple outward flow would create one kind of outer boundary. A turbulent magnetic outflow creates another. If the field is folded, tangled, or variable, then particles moving through it do not experience a neat, steady channel. They can be scattered. They can be guided differently. They can find paths inward or be pushed away depending on energy, direction, and magnetic structure. That changes how the solar domain filters energetic particles coming from beyond the sun. The outer edge of the heliosphere may sit far from the corona, but its behavior is connected to what begins close to the star. A weakness, disturbance, or pattern born near the sun can travel outward through the solar wind. Over time, that structure becomes part of the pressure system that holds interstellar material at a distance. This is why the sun's own complexity cannot be separated from the question of interstellar weather. The outside medium presses inward. The sun answers with this wind that is not steady, not flat, and not perfectly predictable. Picture the corona for a moment as a place of restless magnetic architecture. There is no solid surface where the wind simply begins like steam from boiling water. Instead, magnetic loops rise, open, snap into new arrangements, and guide charged particles outward into space. The light is fierce, but the important motion is not only brightness. It is structure. It is the way invisible fields decide where matter can escape and how that matter carries the sun's influence with it. From far away, the solar wind can sound like one continuous stream. Up close, it is more like a current filled with bends, reversals, and shifting channels. That is the hidden complication Parker Solar Probe exposed. It showed that the sun's outward pressure is not just a matter of strength. It is also a matter of organization. A strong flow that is highly tangled may filter particles differently from a weaker flow that is more orderly. A magnetic field with sudden reversals may change how energetic particles move through the inner solar system. A wind filled with internal structure may create an outer boundary that changes in ways older, smoother models could not fully capture. Some researchers have also asked whether the surrounding interstellar environment might influence the sun's behavior over long periods. That idea must be treated carefully. The sun has powerful internal cycles of its own. Its magnetic activity can vary for reasons rooted inside the star, without needing an external cause. Current understanding does not allow the interstellar medium to be presented as the confirmed driver of solar variability. At most, it remains a contested possibility in a much larger and more difficult problem. The measured part is already enough. The solar wind is structured at its source. Its magnetic field can fold back on itself. Its turbulence can shape how particles move. And its behavior near the sun can echo all the way to the distant edge where the sun's influence finally gives way. The shield around the planets therefore depends on something less simple than an outward blast from a star. It depends on a magnetic wind with hidden texture, born in the corona and stretched across the solar system. The outer boundary may be tested by interstellar pressure, but its first uncertainty begins much closer to home. It begins in the uneven wind of the sun. The forecast we cannot make yet begins with a strange limitation. Scientists can measure the solar system's outer boundary better than ever before, yet they still cannot see the exact interstellar conditions waiting ahead. They can feel parts of the weather at the edge. They cannot yet produce a clear radar image of the route in front of the sun. That is not because the process is imaginary. It is because the medium around the solar system is thin, distant, structured, and difficult to measure from inside the very bubble being affected. Interstellar weather is not weather in the earthly sense. There are no clouds rolling across a sky. There is no rain, thunder, pressure front, or visible storm line. Here, the word points to gas density, particle flow, magnetic direction, energetic particles, and small changes in material spread across enormous distance. Those properties can shift from one region to another. The gas between stars can become more or less dense. The flow of atoms can change direction. Magnetic fields can strengthen, weaken, or bend across the surrounding medium. Particles can arrive from distant sources and interact with the sun's own outflow. Together, those conditions decide how strongly interstellar space presses against the sun's domain. Researchers already have several ways to infer what surrounds us. They measure neutral atoms entering the heliosphere from outside. They study how distant starlight changes as it passes through thin gas before reaching telescopes. They use particle maps built from energetic neutral atoms that return from the boundary. They compare those indirect maps with the narrow direct paths recorded by the Voyager probes. Each method adds one part of the picture. None of them gives the complete shape of what lies ahead. This is the central problem. The solar system is moving through the local interstellar environment, but the fine details of that environment are not mapped like roads on a planet. A denser pocket could be missed until its effects become easier to measure. A shift in magnetic direction could matter long before it looked dramatic in any model. A subtle change in incoming particles could alter the outer boundary without leaving a simple visual sign. The scale makes the problem even harder. To predict the next long stretch of interstellar conditions, scientists would need to understand material spread across distances far beyond the planets. They would also need to know how that material is arranged on smaller scales, because small structures can matter when the heliosphere moves through them. It is like trying to forecast the weather across a continent while standing inside a single drifting tent. The wind at the fabric tells you something. The pressure against one side tells you something. But the shape of the weather beyond the fabric remains partly hidden. That is why other stars are useful. Many stars have their own astrospheres, protective wind bubbles formed when stellar outflows meet the interstellar medium around them. By studying those distant systems, researchers can see how a star's wind responds under different surrounding conditions. Some astrospheres appear compressed. Some stretch into asymmetric forms. Some show bright interaction regions where the star's motion and the outside medium produce a visible signal. These examples do not give a direct forecast for the sun. They do something almost as important. They show the range of possible responses when a star moves through a changing galactic environment. The sun is not unique in having to negotiate pressure from the space between stars. It is simply the one case where Earth sits inside the result. Larger maps also help place the solar system within the galaxy's energetic setting. Gamma-ray observations can reveal regions where high-energy particles interact with gas and radiation. Studies of cosmic rays help scientists understand where some of those particles may come from and how magnetic fields shape their motion. These tools widen the context, but they do not replace local measurements. A galaxy-scale view can show the broad environment. It cannot tell us every fold, pocket, and boundary condition that will meet the sun's protective domain. That is why future missions matter. A dedicated interstellar probe could travel far beyond the planets, with instruments designed from the beginning to study the heliosphere and the medium beyond it. Outer heliosphere sensors could provide more than isolated tracks through the boundary. A wider network would help scientists compare different directions, different particle populations, and different magnetic conditions at the same time. The goal would not be to confirm a disaster. The goal would be to improve resolution. Better measurements could reveal whether the solar boundary is tightening, shifting, or changing shape in ways current instruments can only partly detect. They could show how incoming material varies across direction. They could help separate changes caused by the sun from changes caused by the interstellar environment around it. For now, the picture remains powerful but incomplete. Humanity has touched the boundary with aging spacecraft. It has mapped returning particles from near Earth. It has read starlight filtered through gas between stars. It has compared our star with distant stars moving through their own surrounding media. Yet the exact small-scale structure ahead of the sun remains beyond current sight. The problem is not ignorance. It is resolution. Scientists know the solar system is moving through real interstellar material. They know the heliosphere responds to pressure, particles, and magnetic fields. They know that the boundary is not simple. What they do not yet know is the full shape of the weather ahead. And until that shape becomes clearer, every forecast remains a careful outline drawn around missing detail. A long crossing is the right way to understand what is happening around the solar system. This is not a disaster arriving tomorrow. It is not a sudden wall in space. It is not a countdown. It is a slow movement through a surrounding medium, across spans of time far longer than any civilization has existed. That scale changes the meaning of the risk. When something unfolds across centuries, thousands of years, or longer, it can be easy to ignore because it does not feel urgent. But the opposite mistake is just as dangerous. It can be turned into an alarm before the evidence can support that alarm. The responsible position sits between those extremes. It begins with measurement. Long-term planetary risk cannot be understood through fear, and it cannot be understood through dismissal. It has to be watched carefully with instruments that can outlast short attention spans, political cycles, and temporary funding priorities. The solar system's outer environment belongs in that category. It is slow enough to study. It is distant enough to underestimate. And it is connected enough to matter. The practical reasons are already clear. Astronauts traveling beyond Earth's magnetic field depend on accurate knowledge of the radiation environment. Spacecraft electronics can be damaged by energetic particles. High-altitude aviation, satellite operations, and future deep space missions all depend on knowing how particle conditions change. The chemistry of the upper atmosphere matters for ozone. Ozone matters for ultraviolet radiation. Climate models improve when they include the right background conditions, even when those conditions are only one part of a much larger system. Agriculture, technology, and human planning all rest on the assumption that Earth's environment will remain within certain limits. Those limits are not shaped by Earth alone. They are shaped by the sun, by the planet's magnetic field, by the atmosphere, and by the interstellar medium through which the sun is moving. Preparation does not require panic. It requires a wider idea of planetary stewardship. Usually that phrase brings to mind oceans, forests, energy use, pollution, and climate. Those concerns are immediate and human. They remain close to the surface of daily life. But Earth also has a cosmic environment. It has a radiation environment. It has an upper atmosphere connected to space. It has a magnetic shelter that changes over time. It sits inside the sun's larger domain, and that domain is pressed by the material between stars. This does not make human choices meaningless. It makes the picture larger. A civilization that learns to monitor its own atmosphere should also learn to monitor the space that touches that atmosphere. A civilization that sends crews beyond low orbit should understand the particle conditions waiting beyond Earth's magnetic protection. A civilization that depends on satellites should care about the invisible weather that can disturb electronics far above the ground. The instruments already sent into space are the beginning of that awareness. The Voyager probes gave direct measurements from beyond the solar boundary. The interstellar boundary. Explorer mapped particles returning from the outer interaction zone. Parker Solar Probe measured the solar wind near the place where it is born. Each mission holds one part of a growing picture. None of them completes it. That incompleteness is not failure. It is the normal state of a young science reaching beyond its first clear horizon. For most of human history, the space between stars was an idea more than an environment. It belonged to distance, myth, mathematics, and light. Now it has pressure. It has particles. It has dust. It has magnetic structure. It has measurable effects at the edge of the sun's influence. And because our planet travels inside that influence, the study of interstellar space is also the study of Earth's extended surroundings. Picture the solar system moving onward through the dark. There is no visible hull around it. No bright ring marks the edge where the sun's wind begins to lose control. No one on Earth can look up at night and see the pressure of the galaxy against our star's outer domain. Yet instruments listen from different parts of the system. Old spacecraft whisper from beyond the boundary. Particle maps return clues from the edge. Solar probes watch the wind take shape near the star. Together they form a kind of quiet awareness, spread across millions and billions of miles, trying to read the conditions around the vessel while it is still moving. That is the final shift in perspective. The solar system is not a closed clockwork of planets circling safely in empty space. It is a moving structure inside a larger environment. The sun protects, but it also negotiates. Earth is sheltered, but it is not separate. The galaxy is distant, but not disconnected. And for the first time, one species on one planet has begun to measure the pressure of the dark around its own star.